In question 1, we've got f of x defined here, and we need to show that it can be written in this form with a, b, and c being integers to be found. Well, the obvious thing to do is start by long division. So we've got 2x cubed plus 0x squared minus 4x minus 15, which is the numerator, to be divided by x squared plus 3x plus 4, which is the denominator. Well, notice that I've placed the 0x squared term as a placeholder so that when I do my long division, everything is in place. So remember, we're trying to match the highest order term on the left. So the x squared should be multiplied by 2x to get 2x cubed plus 6x squared plus 8x, and we deduct, and we get 0x squared minus 6x squared is minus 6x squared, and then it's minus 4x minus 8x, which is minus 12x minus 15. So I need the minus 6 here, so minus 6x squared minus 18x minus 24, and I deduct once more, and I get 6x plus 9, and therefore we have that f of x can be written as 2x minus 6 plus 6x plus 9, which is the remainder, over the divisor of x squared plus 3x plus 4. Well, I can proceed into factorizing the 6x plus 9 to match the form of the answer I need to arrive at. So we've got that f of x is 2x minus 6 plus 3 brackets 2x plus 3 over the x squared plus 3x plus 4, and therefore we conclude that a is 2, b is negative 6, and c is 3. In part B, we need to evaluate the given integral, giving our answer in the form p plus ln q, with p and q being integers. So we've got the integral from 3 to 5 of f of x dx, which according to the answer of part A is the integral of 2x minus 6 plus 3 times 2x plus 3 over the x squared plus 3x plus 4 with respect to x from 3 to 5. Well, we know that the integral of 2x is simply 2x squared over 2. The integral of negative 6 is minus 6x. And for the integral of the fraction here, we notice that the derivative of the denominator, the derivative of x squared plus 3x plus 4, is 2x plus 3. And therefore, this can simply be written as 3 ln of the denominator of x squared plus 3x plus 4. And I've got limits from 3 to 5. Well, the 2x squared over 2 is simply x squared. And I will start by substituting the upper limit of 5. So this is going to be 5 squared minus 6 times 5 plus 3 ln of 5 squared plus 3 times 5 plus 4. And I will now substitute the lower limit. So I've got 3 squared minus 6 times 3 plus 3 ln of 3 squared plus 3 times 3 plus 4. So this simplifies to minus 5 plus 3 ln of 44 and minus the negative 9 plus 3 ln of 22. So I've got minus 5 plus 3 ln 44 plus 9 minus 3 ln of 22. Well, minus 5 plus 9 is 4, and the 3 ln 44 minus the 3 ln 22 can simply be written as 3 ln of 44 over 22. We know when we've got subtraction of logarithms can be written as the logarithm of the quotient. So this is giving me 4 plus 3 ln 2, which is not matching the form in which I need to arrive at. I need to get p plus ln q. So what I need to do is write this as 4 plus ln of 2 to the power of 3, which is 4 plus ln of 8. We've got the function f defined to be 5 minus 4 over 3x plus 2, with domain x being greater than or equal to 0. And we're being asked to find the range of f. So one way we could do this, even though it's only 2 marks, it's for us to actually sketch f of x. So I will start by considering the cut on the y-axis. So when x is 0, we've got f of 0 being 5 minus 4 over 3 times 0 plus 2, which gives an answer of 3. So we know that this function is cutting the y-axis at 3. I will then proceed with the vertical asymptote. It's the point at which the denominator is 0, and therefore the function is undefined because we're looking at division by 0. So we've got 3x plus 2 is equal to 0. So 3x is negative 2. So x is negative 2 over 3. And for the horizontal asymptote, I'll be considering the behavior of y as x goes to infinity. So as x goes to infinity, we can see that the denominator here becomes infinitely large. So this part is essentially 0 and f of x is 5. So we get that y tends to 5, and therefore the equation of the horizontal asymptote is y is 5. An alternative way of determining the horizontal asymptote is to simply use my calculator, and I will simulate exactly this process of tending towards infinity. So I will be substituting a really big value for my answer key. So I'm just putting lots of 9s there. I'm storing it on my answer key, and then I've got 5 minus 4 over 3 ans plus 2, which is essentially me substituting x with a really large value. I press the equal button and I get 5. So the horizontal asymptote is at y is 5. This means I can now proceed into sketching my graph, my function. So we've got the axis here. We've got asymptotes at minus 2 over 3 for x and y is 5. So the graph should be looking something like this with a cut on the y-axis at 3. In addition, if we take into consideration that the domain is x greater than or equal to 0, it means that we are only looking at this part of the curve. So we can see that the output, the y values that are attainable are from 3 inclusive up to 5 non-inclusive, and therefore we conclude that the range for this is y belongs to the reals, and we are 3 less than or equal to y less than 5. In BI, we need to find f inverse, and I will start by writing f as y is equal to 5 minus 4 over 3x plus 2. We know that when we're trying to find the inverse, we interchange x and y. So this leads to x is 5 minus 4 over 3y plus 2. And the objective is for us to now make y the subject. I could start by multiplying throughout by 3y plus 2, leading to x brackets 3y plus 2 is 5 brackets 3y plus 2 minus 4. I will expand to get 3xy plus 2x is equal to 15y plus 10 minus 4, which leads to 3xy plus 2x is equal to 15y plus 6. I will now be collecting the y terms on the right hand side and the remaining terms on the left hand side. So I've got 2x minus 6 is 15y minus 3xy, and I notice I've got a common factor of y on the right hand side. So 2x minus 6 is y brackets 15 minus 3x. I could also take the 3 as a common factor, but that's not necessary. Remember, the objective is to make y the subject. So this ends up at 2x minus 6 over the 15 minus 3x being equal to y, which means that f inverse of x is equal to 2x minus 6 over the 15 minus 3x. In II, we need to write down the domain of f inverse, and we know that the domain of the inverse is the range of the original of f of x, and we found this in part A. So we've got that the domain is x belongs to the reals, and x is between 3 inclusive and 5 excluding. So this is the domain of the inverse. In C, we need to find f of g of negative pi, so it's a composite function. So we know that we always start from the inside, so it's f of g of negative pi. So I will be evaluating g when x is negative pi. So this is f of the modulus of 4 sine of minus pi over 3 plus pi over 6. So we find that this is f of the modulus of negative 2. When I evaluate the inside over here, all of this gives me a negative 2. Well, the modulus of negative 2 is 2. So this is f of 2, which is 5 minus 4 over 3 times 2 plus 2, which gives an answer of 9 over 2. We've got a sketch of part of the curve with equation x minus 12 squared e to the 3x. We are being told that we have a maximum turning point at A and a minimum turning point at 2, 0 as shown on the diagram. And we need to use calculus, that means differentiation, to find the exact coordinates of point A. So I will start by differentiating. We're looking at the product rule here. So it's the product of x minus 2 all squared and the e to the 3x. So I start by differentiating the first, and the first is x minus 2 all squared. So I get the power down, I deduct 1 from the power times the derivative of the bracket, which is 1, and I keep the second, and then I keep the first, so x minus 2 squared, and I differentiate the second. Well, the derivative of e to the 3x is simply 3e to the 3x. So I notice that we've got a common factor of e to the 3x times x minus 2, and we're left with 2 plus 3 times x minus 2. So this leads to e to the 3x times x minus 2 times 2 plus 3x minus 6. So we've got e to the 3x times x minus 2 times 3x minus 4. Now we know that at point A, being a maximum turning point, f dash of x is equal to 0, which means that e to the 3x times x minus 2 times 3x minus 4 must be equal to 0. So we've got that x minus 2 is 0, or 3x minus 4 is 0. Now we also know that e to the 3x being 0 has no real solutions, because if you sketch the graph of e to the 3x, the y equals to 0 will be an asymptote, and therefore there is no value for x that will actually make e to the 3x being 0. So from x minus 2 is 0, you get that x is 2, which is obviously the minimum point shown on the diagram. And for 3x minus 4 is 0, we get 3x is 4, which means that x is 4 over 3. This is the x coordinate of the point we're looking, the point A. For the y coordinate, I will be substituting into the equation of f of x. So it's 4 over 3 minus 2 all squared times e to the 3 times 4 over 3. This gives an answer of 4 over 9 e to the power of 4. And therefore, we conclude that the coordinates of A are 4 over 3, 4 over 9 e to the power of 4. We're then told that the equation f of x is k. K is a constant, has at least 2 distinct roots, and we need to state the range of possible values for k. Well, I will start by writing down the coordinates of point A, the point we just determined in part A. So we know that the height, the y value, is 4 over 9 into the 4, and we are considering points of intersection with the straight line y equals to k, which is just a horizontal line. We can see here we've got 3 distinct roots, and if I just play a bit with it, if I go above point A, I'll be having just 1 root. If I'm exactly at the height of A, I'll be having 2 roots, so this is a permissible value. And if I go below the x-axis, then I'll be having no roots, whereas if I'm exactly on the x-axis, I only have the root here at 2. So we therefore conclude that for us to have at least 2 distinct roots, it must be the case that k is greater than 0 but less than or equal to 4 over 9 e to the power of 4. In question 4, we've got y being defined to be the log of 2x plus 1 base 10, and we need to express x in terms of y. So starting with the expression we were given, we can simply undo the logarithm by doing 10 to the y is equal to 2x plus 1, leading to 10 to the y minus 1 is 2x, and therefore 10 to the y minus 1 over 2 is equal to x. In part B, it says, hence, giving you an answer in terms of x, find dy dx. So we need to use the result of part A. Well, in order to do that, let me start by reminding you that if y is a to the x, then the derivative is a to the x ln a. Remember, we have already established that x is 10 to the y minus 1 over 2. So instead of dy dx, I will start by finding dx dy. So dx dy is equal to 10 to the y ln 10 over 2, the derivative of 10 to the y. I'm using this rule with a being 10. Well, the derivative of negative 1 is just 0, and the over 2 stays there. and I can proceed into writing dy dx to be equal to 2 over 10 to the y ln 10. So I'm just flipping both sides, so the dx dy is becoming dy dx, and the only thing missing is to replace the 10 to the y with an expression in x, because we're being asked to find dy dx in terms of x. So this is equal to 2 over 2x plus 1, because we have established in part A that 10 to the y is 2x plus 1. So my final answer is that dy dx is 2 over 2x plus 1 times ln 10. In question 5, we've got an expression for the profit made by a company P million pounds T years after the company started trading, and we need to show, according to the model, that exactly a year after starting trading, the company made a loss of approximately £830,000. So because we're looking at exactly a year after the beginning of trading, it means that we need to substitute T is 1. So this leads to P being 4 times 1 minus 1 over 10 plus 3/4 ln of 1 plus 1 over 2 times 1 plus 1 squared, and I will evaluate this. This gives an answer of minus 0.828058. Remember, this is measured in millions of pounds, so we conclude that this is equal to minus 828,058, which simply means a loss of £830,000 as required. A manager of the company wants to know the value of t for which p is 0, and we need to show that this value of t occurs between 6 and 7. So we're looking for a change of sign here. So I will be substituting t is 6, and this gives an answer for p of minus 0.08799, whereas for t is 7, we get p to be 0.1975. And therefore we conclude, we write down that there is a change of sign, and also p of t is a continuous function, hence a root exists in the interval 6 to 7. Notice that you need to mention both the change of sign and the continuity to score the second mark. In C, we need to show that the equation p is 0 can be expressed in this form. So I will start by setting p is 0, which simply means that 4t minus 1 over 10 plus 3 over 4 ln of t plus 1 over 2t plus 1 all squared must be equal to 0. So the first thing to do is to send the 3 over 4 ln on the right hand side, and we get 4t minus 1 over 10 is equal to minus 3 over 4 ln of t plus 1 over the 2t plus 1 all squared. So notice that we need to arrive at something that involves ln of 2t plus 1 squared over t plus 1. So it makes sense to take the negative sign here and take it up as a power over here. This will help me into flipping the expression within the logarithm. So we've got 4t minus 1 over 10 is equal to 3 over 4 ln of t plus 1 over the 2t plus 1 squared, and all to the minus 1, which can be written as 4t minus 1 over 10 is equal to 3 over 4 ln of 2t plus 1 squared over the t plus 1. So at least I'm matching the form within the logarithm I can see in the answer I need to arrive at. And then the next thing to do is multiply by 10, leading to 4t minus 1 is equal to 15 over 2 ln of 2t plus 1 squared over t plus 1. And therefore it's obvious that the next thing is to take the negative 1 on the right hand side, leading to 4t is equal to 1 plus 15 over 2 ln of 2t plus 1 squared over t plus 1. And the final thing to do is, of course, to divide throughout by 4 to isolate t. So we get that t is a quarter plus 15 over 8 ln of 2t plus 1 squared over the t plus 1, so as required. In part D, we need to use the iteration formula given here with the starting value of 6 to find the value of T2 and the value of T6, correct to 3 decimal places. So I'm starting with T1 is 6, and I'm using my calculator to simulate exactly the process. I will start by storing 6 on my answer key, and then I'm writing the iterative formula exactly on my calculator. So it's 1 over 4 plus 15 over 8, and we've got a ln of 2 ans plus 1 squared over the ans plus 1. So the answer key is holding the 6 at the moment, and every time I press the equal sign, it's a new iteration, so it's the next value for t. So if I press it once, I get 6.21997, so 6.21997 dot dot dot. Remember, we're trying to give this to 3 decimal places, so it's gonna be 6.220. If I press it again, it's T3, once more 4, 5, 6, and for T6 we can see that this is 6.314158 dot dot dot, which correct to 3 decimal places is 6.314. And in part E, it says find, according to the model, how many months it takes in total from when we have started trading for it to make a profit. So we've got this on the calculator. If I keep pressing the equal sign, I can see that my value is gradually stabilizing at 6.314 something. So if I simply do 6.314, this is years, and I multiply this by 12 to make it into months, I get 75.8, and therefore we conclude that it will take 76 months for the company to make a profit. In question 6, we've got an expression here for y in terms of x, and we need to show that the derivative dy dx can be written in this form where a, b, and c are integers to be found. So obviously we need to apply the quotient rule here. So we differentiate the top, the 2 plus 3 sine x, which gives me 3 cos x, and we keep the bottom, which is cos x plus sine x, and then we deduct the top, which is 2 plus 3 sine x, times the derivative of the bottom, which is minus sine x plus cos x, and it's all over the denominator square, the bottom squared, so it's cos x plus sine x all squared. I will proceed by expanding. This will give me 3 cos squared x plus 3 cos x sine x plus 2 sine x minus 2 cos x plus 3 sine squared x minus 3 sine x cos x, and all of it over the cos x plus sine x squared. So the obvious next step is to simplify the numerator. We can see that the 3 cos x sine x with the minus 3 sine x cos x will cancel out. I will then group together the 3 cos squared plus 3 sine squared, leading to 3 brackets cos squared x plus sine squared x close brackets plus 2 sine x minus 2 cos x, and I will now expand the denominator, which is gonna give me cos squared x plus 2 sine x cos x plus sine squared x. Now obviously in the numerator we've got 3 plus 2 sine x minus 2 cos x, whereas in the denominator we've got 1 plus 2 sine x cos x. I know we might be tempted in writing 2 sine x cos x as sine 2x. However, notice that in the answer we need to arrive at, we don't have any double angles, it's just x, so I keep it as it is. And for me to start seeing the 2 sine x in the denominator, for example, it makes sense to divide throughout by cos x. So let me divide throughout by cos x and see what we get. This looks promising because I can see the sec x appearing in the denominator as well. So I'm dividing throughout by cos x, and this leads to 3 sec x in the numerator plus 2 tan x minus 2 over the sec x plus 2 sine x, which matches the form which we needed to arrive at. and therefore we conclude that the constant a, the coefficient of tan x, is 2, the constant b, the coefficient of sec x in the numerator, is 3, and c is -2, it's the constant in the numerator. 7, part A, we've got the graph of y is 5 minus modulus of 3x minus 22, and we need to determine the coordinates of the vertex of C1 and the intersection of C1 with the y-axis. Well, let's start with the vertex. We know that the vertex is at the point where the expression within the modulus is 0, so I'm starting by solving 3x minus 22 is equal to 0. So I've got 3x is 22, so x is 22 over 3. So the x coordinate is 22 over 3. And when 3x minus 22 is 0, this just vanishes, and we've got y is equal to 5. That's the y coordinate of the vertex, and therefore we conclude that the coordinates of the vertex are 22 over 3, 5. For the intersection with the y-axis, I'm going to simply substitute x is 0, and we get that y is 5 minus the modulus of 3 times 0 minus 22. So this is 5 minus the modulus of -22, which is 5 minus 22, which turns out to be minus 17. And therefore the coordinates of the cut on the y-axis are 0, minus 17. In part B, we are asked to find the x coordinates of the intersection with the x-axis. So if we are intersecting the x-axis, that means that y is 0, and therefore we are trying to solve 5 minus the modulus of 3x minus 22 is equal to 0. So we've got 5 is the modulus of 3x minus 22, which simply means that the 3x minus 22 could be plus or minus 5. So let's start with the plus case. So 5 is 3x minus 22. So we've got 27 is equal to 3x, and therefore x is 9. And the other case is -5, being 3x minus 22, leading to 17 being 3x, and therefore 17 over 3 is the other cut on the x-axis. In part C, we are asked to sketch the curve C2 with equation y is 1 over 9x squared minus 9, and notice that we need to identify clearly the coordinates of any points of intersection with the coordinate axis. Well, obviously we're looking at a parabola. The shape is a smiley one because the coefficient of x squared is positive. So we're looking at y is 1 over 9 x squared minus 9. I will start with the cut on the y-axis. So when x is 0, we can see that y is -9. And I will proceed with the cut on the x-axis. So I'm putting y is 0, which means that 1 over 9 x squared minus 9 is 0. Which leads to 1 over 9 x squared is 9, and therefore we've got that x squared is 81, and therefore the cuts are at plus or minus 9, which means I can proceed in sketching the graph here on the given diagram. Before doing that though, I will write down the coordinates of the cuts on the axis for the curve C1. So it was the 17 over 3 and the 9 on the x-axis and the minus 17 on the y-axis. So if I draw the parabola here, it should look something like this. So we've got the same cut on the x-axis in the positive. So at 9, we've got a cut at -9, and we're cutting the y-axis at -9, which is obviously higher above the minus 17. In part D, we are asked to find the coordinates of the points of intersection of C1 and C2. So I will quickly revisit my diagram here, and I will identify each line segment with its individual equation. So on the right hand side, we've got y is 5 minus brackets 3x minus 22, which is 5 minus 3x plus 22. So we're looking at y is 27 minus 3x, whereas on the left hand side, this one here has equation y is 5 plus the 3x minus 22. So this is y is minus 17 plus 3x. So to find the points of intersection, I will simply equate each of these straight lines with the parabola, and I will be picking out the solutions that match what I see on the diagram. So when I equate the minus 17 plus 3x with the 1 over 9x squared minus 9, I will pick the solution that lies between 0 and 17 over 3. Whereas for the y is 27 minus 3x equated with 1 over 9x squared minus 9, I can simply see from the diagram that the solution is going to be 9. So I'm equating negative 17 plus 3x with 1 over 9x squared minus 9. The first thing to do is multiply throughout by 9 to get rid of the fractions, leading to minus 153 plus 27x is x squared minus 81. I will be collecting everything on the right hand side, leading to 0 is x squared minus 27x plus 72, and I'll be using the quadratic formula to determine the solutions. So we've got x is minus negative 27 plus minus the negative 27 squared minus 4 times 1 times 72 all square root and all divided by 2a, which is 2 times 1. We get solutions of 24, or x is equal to 3. So for 24, we can see that it is not within the range of values from the graph. So we reject, we say it's not valid, and we proceed with the solution of x is 3. So I'm going to find the corresponding y coordinate. So y is going to be 1 over 9 times 3 squared minus 9, which gives an answer of negative 8. Now the other solution, I could simply state this by looking at the graph. It's at x is 9, which means that y is 0. And therefore we conclude that the 2 points of intersection have coordinates 3, negative 8, and 9, 0. In 8a, we are asked to express 8 sine x minus 15 cos x in the form r sine x minus alpha, where r is positive and alpha is in radians between 0 and pi over 2. And we need to give the exact value of r and the value of alpha in radians to 4 significant figures, where I will start with 8 sine x minus 15 cos x being equal to exactly what I was given, r sine of x minus alpha. I will be using the compound formula for sine a plus b to expand the right hand side into r sine x cos alpha minus r cos x sine alpha, and then I will be equating the sine x terms. So the 8 sine x is equal to the r sine x cos alpha, and the cos x terms, the 15 cos x is equal to r cos x sine alpha, which leads to 8 being equal to r cos alpha and 15 being equal to r sine alpha. This simply means that 8 over r is equal to cos alpha and 15 over r is equal to sine alpha. I will then proceed by drawing a right angle triangle. The angle alpha is at the base, so we've got the cos alpha being adjacent over hypotenuse and sine alpha being opposite over hypotenuse. So I'm using Pythagoras to get r. It's 8 squared plus 15 squared square root, which gives 17. And we can also see that tan alpha is 15 over 8. Therefore, alpha is shift tan of 15 over 8. Remember, we are in radian mode here, and we get that alpha is 1.081, which means that we have that 8 sine x minus 15 cos x is equal to 17 sine of x minus 1.081. In part B, we're given f of x here, and we're asked to find the minimum value of f of x and the smallest value of x at which this minimum value is attained, where there is a distinct, a clear connection with part A. And we can see this if we write f of x as 15 over the 41 plus, I will factor out the 2, and I've got 8 sine x minus 15 cos x. And the expression within the bracket is what I have written in part A as a single sign. So this can be written as 15 over the 41 plus 2 times the 17 sine of x minus 1.081. So this is simply 15 over 41 plus 34 sine of x minus 1.081. Remember, we're trying to determine the minimum value. Well, we know that the sine of any angle varies between plus minus 1, and therefore 34 sine will vary between plus minus 34. And hence, for the minimum value of f of x, we need to make sure that the denominator is a maximum. So it's going to be 15 over 41 plus 34, which gives an answer of 1 over 5. Now for the smallest value of x at which this minimum value occurs, we need to essentially find the value of x that will make sine of x minus 1.081 being equal to 1. Remember that x had to be positive, so we're looking for the first positive solution. So we're solving here sine of x minus 1.081 is equal to 1. So x minus 1.081 is shift sine of 1. So x minus 1.081 is pi over 2, which leads to x being 2.65 corrected to decimal places. In part C, we are asked to state the y-coordinate of the minimum points on the curve y is 2f of x minus 5. Well, we have found the minimum of f of x to be 1 over 5, so I will simply do y is 2 times the minimum of 1 over 5 minus 5, which gives an answer of minus 23 over 5. We're essentially looking here at two transformations. The y's get multiplied by 2 and then we deduct 5. So that's exactly how the minimum will be affected. Therefore, we got an answer of minus 23 over 5. In part D, we are asked to state the smallest value of x at which a maximum point occurs for the curve with the equation y is minus f of 2x. Well, let's start by considering what transformations we're dealing with. Well, the 2x here means that the x's are divided by 2, whereas the negative sign outside simply means that we're multiplying the y by negative 1. This is equivalent to a reflection along the x-axis, which means that the maximum points become minimum points and vice versa. Therefore, we can see that the value of x will only be affected by the 2x here, so it's going to be divided by 2, and therefore we conclude that x will be 2.65, the value we obtained before, divided by 2, which gives an answer of 1.33. In 9a, we need to prove the given identity here. So when I'm proving identities, I need to show all baby steps to justify either going from left to right or from right to left. Or if I'm going to go from the left-hand side to a certain point, I need to show that the right-hand side also arrives at this point. So in this case, I will start from the left-hand side. It's cos squared over cos 2 theta minus sine 3 theta. I see that I need to arrive at something involving theta only. So the first thing to do is maybe write the cos squared as 1 minus sine squared, and in the denominator the cos 2 theta can be written as 1 minus 2 sine squared theta, whereas for the sine 3 theta I can think of this as sine of theta plus 2 theta. So this is 1 minus sine squared theta over 1 minus the 2 sine squared theta, and I will now expand the sine theta plus 2 theta. So this is sine theta cos 2 theta plus cos theta sine 2 theta, which leads to 1 minus sine squared theta in the numerator, and in the denominator we've got 1 minus 2 sine squared theta minus the sine theta. For the cos 2 theta, I will write this as 1 minus 2 sine squared theta plus the cos theta and the double angle for sine 2 theta, which is 2 sine theta cos theta. So at least now I'm only dealing with thetas. The problem is that I have cos theta and sine theta. So let's see where the simplifications will take me. I've got 1 minus sine squared theta in the numerator still. And in the denominator, we've got 1 minus 2 sine squared theta minus the sine theta minus 2 sine cubed theta plus 2 sine theta cos squared theta. So this can be written as 1 minus sine squared theta over the 1 minus 2 sine squared theta minus sine theta plus 2 sine cubed theta minus 2 sine theta cos squared theta. And then I know that I need to arrive at an expression involving only sine thetas. So the cos squared theta here can be written as 1 minus sine squared theta. So this leads to 1 minus sine squared theta over the 1 minus 2 sine squared theta minus sine theta plus 2 sine cubed theta minus 2 sine theta, and then brackets 1 minus sine squared theta. So we've got 1 minus sine squared theta over the 1 minus 2 sine squared theta minus sine theta plus 2 sine cubed theta minus 2 sine theta plus 2 sine cubed theta. So I'll put everything nicely together. I will also factorize the numerator. So the numerator is a difference of two squares, which is 1 minus sine theta times 1 plus sine theta over the denominator, which simplifies to 1 minus 3 sine theta minus 2 sine squared theta plus 4 sine cubed theta. Well, looking at what we need to arrive at the given identity, we've got on the right hand side 1 plus sine theta in the numerator, which means that the 1 minus sine theta should disappear. And the only way for it to disappear is if there is a common factor of 1 minus sine theta in the denominator. So this can be written as 1 minus sine theta times 1 plus sine theta over the 1 minus sine theta. So I'm forcing a factor of 1 minus sine theta, and I'm trying to figure out what will be the other bracket. So I need to get the 1 here. So 1 times 1 will give me the 1 I'm after. Now I want to get minus 3 sine theta. So minus sine theta times 1, I get minus sine theta. I need minus 3 sine theta, which means I need a minus 2 sine theta. For it to give overall the minus 3 sine theta, it's the minus sine theta and the minus 2 sine theta. And then for me to get the last term, the 4 sine cubed theta, it surely means that I want the minus 4 sine squared theta term here. So the 1 minus sine theta with the 1 minus sine theta cancels out, and I'm left with 1 plus sine theta over the 1 minus 2 sine theta minus 4 sine squared theta, which is exactly the right hand side as required. In part B, we're asked to solve for theta between 0 and 360 degrees, the given equation here. So obviously the left hand side here can be written using the identity we've proved in part A as 1 plus sine theta over the 1 minus 2 sine theta minus 4 sine squared theta, and this is equal to 2 cosec theta, which will be written as 2 over sine theta. I will proceed with cross multiplying, so we've got sine theta brackets 1 plus sine theta is equal to 2 brackets 1 minus 2 sine theta minus 4 sine squared theta. I will expand to get sine theta plus sine squared theta is equal to 2 minus 4 sine theta minus 8 sine squared theta, and I will collect everything on the left hand side to get the 9 sine squared theta plus 5 sine theta minus 2 is equal to 0. We have obtained the quadratic in sine theta, so we've got that sine theta is minus b plus minus b squared minus 4ac and all square root and divided by 2a. So this gives answers of sine theta being equal to negative 5 plus root of 97 over 18, which is 0.26938 ... or a second solution for sine theta, which is negative 5 minus the root 97 over the 18, which is equal to negative 0.8249 ... I will be finding the corresponding principal values. So for the first one, the PV is shift sine of 0.26938 ... which gives an answer of 15.627, and therefore we've got that theta is the PV, the 15.627 plus 360k, or 180 minus the PV, the 15.627 plus 360k, whereas for sine theta being minus 0.8249, the PV is found by doing shift the sign of negative 0.8249 dot dot dot. So this gives an answer of minus 55.582 dot dot dot, and therefore we've got that theta is the PV plus 360k. Remember, the 360k is because of the periodicity of the sine wave, or 180 minus the PV plus the 360k. K attains integer values, positive, negative, or 0. I get an answer for theta which is 15.6 and also 164.4. Whereas if I put k to be 1 here, I get 304.4. And if I put k to be 0 in the last equation, I get 235.6, a total of 4 solutions for this trigonometric equation.